Alrighty guys, hopefully you guys can hear me. There's a lot of background music. So question number 28, here we go. What can be stated about the following reaction in regards to the total number of reactants and products? This one's actually pretty simple. The great thing about this equation, it's already balanced. So if you look here, you have 9 iron, you have 3 times 3 is 9 iron, 3 times 4 is 12 oxygen, 8 aluminum, and then you have 8 aluminum over here, so that's the same, 12 oxygen, so that's the same, and then 9 iron. So what can be stated is reactants, which are on the left here, equal products. So the total number of atoms is the exact same from the reactants to the products. All right, question number 29, whoop-de-daisy. We're gonna do a whole group lesson. Stay tuned when I get back. I just wanna make sure I explain it thoroughly. So we'll cluster for that one and then we'll go from there. All right, my dudes, here we go, number 30. All right, we're getting there. Alright, a solution is made by dissolving some salt in a beaker of water. What is the salt and what is the water? Here we go. Salt. Refresh your memory. Here is the solute. The water equals the solvent. Remember, the solvent dissolves things. The solute is the solid or the thing that's being dissolved. This plus this is a solution. Hot dog. All right. Sweet. So describe the effect each has on how fast a sugar cube will dissolve in water. The speed of stirring will increase how it dissolves. The temperature, if the temperature increases, so too will the rate of solvation, or the rate at which it dissolves. All right. Surface area, crushed versus cube. If you have a crushed ice cube, you have more surface area, you have more pieces being exposed, and so therefore that will increase. So surface area. So a crushed cube will dissolve faster than a whole cube. And then I will actually explain this one in great detail by doing one of my magnificent drawings on the whiteboard, or perhaps even the window. All right, number 32, molarity. Here we go. Can you see it? No, not you, bro. All right, cool. All right, number 32, what is the molarity of NaNO3? Okay, perfect. What is the molarity of a NaNO3 solution made with 25 liters and 160 grams of sodium nitrite? All right. So before we even jump right into this puppy, I'm going to say molarity equals moles divided by liters. Now I'm going to hit the pause button. I'm going to ninja you real quick. Actually, no, I won't. Not yet. So now what I do is I go ahead and underline my variables. So I know I have liters, so that's pretty simple. I have 25 liters. Now I need moles, but hold the phone. We don't have moles, but we do have grams, right? Grams. So can we go from grams to moles? We certainly can. Welcome back, stoichiometry. We missed you. 160 grams of NaNO3 over 1. If we have G's of NaNO3 on the top, we're going to need grams of NaNO3 on the bottom. And then that's going to give us moles of NaNO3. Pardon my tiny writing here. And so what I'm going to do is I'm going to hit the pause button, and you're about to get ninja'd. All right, molar mass is 85, right? 85 moles. And now we multiply this over across. And actually, I made a mistake here. This should actually be down here. Sorry about that. It is 1 in the morning. All right, so if I do this particular problem here, I think it's 1.88. So 1.88 moles. And now I divide that puppy right there, and if I do that, I get 0.075 capital M. That is my answer right there. Bam. If you guys have any questions, please do not hesitate to ask. let's move on to the next one. How many moles of KCl are present in 1.54 liters of a 0.568 molar solution? Holy cheese whiz. So let's go back to our original formula here. Capital M is equal to moles divided by liters, right? Let's underline the variables that are given to us. So we already have liters, that's pretty sweet. And we already have moles, that's interesting. So we have 0.568 capital M is equal to, we don't know what moles is, right? So that's going to be X over 1.54 liters. Now, if we're trying to solve for X, we can do one of two things. We can put a 1 over here and cross multiply, or if we're trying to solve X, right, get X by itself, if we're dividing by 1.54 liters, we can just multiply by, am I recording? Yep, we can multiply by 1.54 liters on both sides. And then I'm going to get 0.87 moles if I do that, and here's my answer. Wowee. Oh, let me slide it over. There you go. Awesome. Sorry about the sloppy handwriting there, my friends. I should have left you guys more space, perhaps next year when you guys retake the class. Alright, how many liters are needed to make 3.33 molar solution using 4.6 or 46.2 moles? Awesome. So let's do the exact same thing. They already give us the moles, right? So I'm going to do 3.33 M is equal to 46.2 moles over, we don't know what liters is, so that's X. And I'm going to show you guys a different way to do it as well if you ever get this funky number down here. So this is the same thing, and in order to solve for X, I'm going to multiply this by this and this by this and set it equal to one another. So I get 3.33X is equal to 46.2 times 1, which is 46.2. Now you just divide both sides by 3.33, and then you guys can figure that out, right? Cool. All right. Ooh, my fave. Here we go. Cheese whiz. What am I gonna do with myself? All right. So if we have 3.45 liters and we have a molarity, capital M, of 1.75, how many grams of NaOH are needed? So we're gonna do it again, right? So if we have 1.75 liters over 1 is equal to some X variable over 3.45 liters, right? We can do the same thing, multiply both sides by 3.54, or we can do this way too, where we multiply across this way, or I should say diagonal. Awesome. So X times 1 is X, so X is equal to 3.45 liters times 1.75, and then I'm going to go ahead and that would be, where am I here? That would be this, right? So 5.175 moles of NaOH, but you don't want moles, you want the grams right here. So you're gonna have to convert to grams. Here we go, once again. Bam, 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 bam. If you have moles up here, you need moles down here. So I'm gonna have 1 mole of NaOH, and then the molar mass of that is, oh man, what was it? Hold 39.97, which is the same thing as 40 grams of NaOH. Please multiply that across and you get your answer. Now let's flip to the good stuff over here. All right. So, I'm going to have a small group on this one right here as well. So number 36. All right. So what is the range on the pH scale for an acid? So I will do this whole thing on Monday. But if you don't want to wait till Monday, actually I may do it on Wednesday. But if you don't want to wait till Wednesday, I'm going to do it right now actually, since we still have plenty of time. What is the range of pH of the pH scale for an acid or base? Draw the pH scale. So it is, bam, it goes from 0 to 14. 7 is neutral. Anything from here this way is an acid. As you get closer to 0, it becomes a super duper strong acid, like HCl has a pH of 1, I believe. 7 is neutral. That could be water, is a very neutral thing. Speaking of water, I'm going to take a sip here. Okay, and then as you go from this way, it becomes very basic, or base, right? 14 is the strongest base, and then 0, of course, is the strongest acid. I'll give you guys examples of this stuff once we go over it. So which one is more acidic, 4 or 6? Remember, as you get closer to 0, it becomes more acidic or stronger, so it would be a pH of quattro, or 4. Draw a diagram that best represents the dissociation of HCl in water. Okay, dissociation is a fancy term for dissolve, right? So it splits apart. Now, here we go. Okay, so what I'm going to do is I'm going to draw a little sweet diagram here. And so this is HCl, right? So we're going to draw H as this one, and then Cl as this one right here. And then we're going to draw H here, and then Cl as this, right? They kind of look like little, I don't know what they look like at 1:30 in the morning. Alright, so they look like that, right? So you have the Cl here and the H here. When they dissolve in water, or they dissociate, you have this. Bam, 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 bam. So what happens? The atoms completely separate and they dissolve in water. So the water kind of pulls them apart. Okay? Now, what is water's role when HBr dissolves into water? What happens with the H plus ions? Remember, HBr, that's a sweet acid, right? Now, if I have HBr, remember the definition of an acid is it donates hydrogen, right? So if I add a little bit of H2O here, it's going to donate this puppy right here to water, right? And so water is this is the acid. Oh, welcome back. Here, this is the base. Water is going to be a base in this situation. And then when they react, of course, this becomes H3O. And then Br is kind of left by itself, right? And so what happens is water receives and acts as the base because it receives hydrogen, right? Now, this would be Br2. We're going to go over what diatomic atoms are, or elements are. So please do not freak out about that in particular, not just yet at least. All right, so here we go. What type of ions are produced when acid dissolves in water? H plus. What type of ions are produced when base dissolve in water? You got the OH negative here. Perfect. Okay. The reason why I said I was going to have a huge lesson on this puppy right here is because this is going to get rather confusing. Acids work on a logarithmic scale. Bases work on a logarithmic scale as well. So, a pH of 2 is 2 times stronger than that. So, the way we write this is the amount of H plus ions, you're going to have a lot of them released, right? And so you're going to have 10 to the negative 2 power. Now, if you have 7 released, you're going to have 10 negative 7. And if you have 10, you're going to have 10 to the negative 10. Now, remember when I told you guys the closer you get to 0, the stronger the pH is, or stronger the acid is? Now, which one is the biggest number? 10 to the negative 10 or 10 to the negative 2? The answer is 10 to the negative 2. Right? And now, when we do pHs, we have to do the complete opposite for this particular one, right? And so, what I mean by that, and I'll give you guys a table for that, is I mean, if I have a pH of 1, kind of butchered that. So if I have a pH of 1, I know that for my hydrogens, my H plus, it's going to be 10 to the negative 1. Now, the opposite is going to be set for the base. And so, if I were to do this particular problem here, the OHs, right? So the OH negative would be, let's see, 2. That would be 10 to the negative 13, 10 to the negative 13. And then if I had a pH of 2, it would be 10 to the negative 2, and this would be 10 to the negative 12. Remember, the only difference is you're going backwards from a scale of 14. And so if you had this one, it would be 10 to the negative 12, right? And if you had 7, well, that's going to be the exact same, because 7 minus 14, or 14 minus 7 is still negative, still 7. And so we're going to do that. And then if you have a pH of 10, this particular one is going to be 10 to the negative 4, right? Because it's always off of a pH scale of 14, or a logarithmic scale of 14 as well. If this is confusing the heck out of you, do not worry. We will go over this as a class. And once you get a couple practice problems in there, you'll be totally fine. All right. Describe the difference between a weak acid and a strong acid. I will give you this. A weak acid, a W, partially dissociates, or I'm going to write dissolves, in water. A strong acid completely dissolves in water, right? Okay. And so which picture, now the reason why this is so is if you're a strong acid, the first thing you want to do is get rid of your H, right? And so if you're a super duper strong acid, you're going to get rid of your H immediately. But if you're a weak acid, you're going to get rid of your H not quite as quickly as you would the strong acid. And so that's the reason why this partially dissolves. So which picture illustrates a strong acid? Right, so remember here, let's look at beaker B. They're still attached, right? Let's look at beaker C. Some of them are completely dissociated or dissolved, but these ones right here, these ones are here, these ones are here are still intact. And if we look at beaker A, all of them are completely dissolved and separated, so this puppy right here would be your strong acid. Your weak acid would probably be this one right here, because part of it dissolves, right? This one, this one, this one, this one, this one, but part of it does not, right? So this is your strong, S for strong, and this is your weak, so upside down, W for weak, right? This concludes this particular video.